Okay, we are almost finished with the mathematical foundation of all the Fourier stuff we're going to need for the rest of the course. There's just one more really interesting and really important property of the discrete Fourier transform that I want to go over. And it's how does it play with convolution. So if you remember, convolution is what happens when you take a signal and then you take another signal. The second signal is thought of as an impulse response. What that means is the second signal contains a bunch of samples, and the time index of the sample can be thought of as a lag, and the value of the sample can be thought of an amplitude, of a return. So what this really is, the impulse response is kind of like an echo signal. So I'm saying, okay, at a lag of 140, it should be an amplitude of 0.7. And so you just take a bunch of lags of the original signal, line them up with where the echoes occur, and then add up the superposition of all of them. And so that's the convolution of this signal with this impulse response. Now in the homework for the vocoder, what I'm showing you is that you can make a vocoder by doing a convolution with a comb signal, right? So if I have this happy voice, birthday to you, happy birthday, which is very monotone, but then I convolve little chunks with different comb signals. So I take the convolution with little combs, and I vary the width between the teeth to control the pitch. I can actually turn this into happy birthday a pitched sound. Happy birthday to you. Happy birthday. And actually what it really is, it's kind of like a singing instrument. In this case, it's a bit like a singing oboe or a woodwind instrument with a reed. We talked about how a comb filter was really like a reed instrument where the noise that you start with, if you put noise into it, that's sort of like blowing into the reed, the randomness, and then the comb spikes are saying, well, once the sound is in the instrument, in the chamber, it bounces back and forth, so you get these periodic lags. But you continue to stimulate with noise. In this case, I'm stimulating with the voice, and I'm getting something that sounds a bit like a wind instrument that's singing. Happy birthday to you. Happy birthday to... Okay, but I also was showing in this assignment, if you take the short time Fourier transform of a tune, like some instrument carrying a tune. So in this case, this is a distorted brass sound. And here's the spectrogram, so showing the short time Fourier transform magnitude, the non-redundant first half of them. So showing that the frequencies over time, their amplitudes. And also take the voice short time Fourier transform. So I do some more voicing.
Work it harder, make it better, do it faster, makes us stronger more than ever.
So then if I take the amplitudes of the voice spectrum, and at each Fourier window I multiply all those amplitudes by the complex coefficients in the instrument spectrogram, I get this, kind of a mix between the two. So it's this, all these complex numbers times the amplitudes here at each frequency in each window. The result I get, it actually sounds like a singing version of that distorted brass.
Work it harder, make it better, do it faster, makes us stronger more than ever.
So what's interesting is it seems like two very different ways of getting a singing wind instrument. So one of them is to do a convolution with this comb filter with periodic spacing. The other one is to do multiplication in the frequency domain. So taking the short time Fourier transform, doing a multiplication, and then doing the inverse short time Fourier transform to go back to the time domain. But what I'm going to show you in this module is that these are actually the same thing, which is very interesting. So let's dive into that. Now, I just reviewed the formulas here for the discrete Fourier transform and the inverse discrete Fourier transform using the complex numbers. So here's the dot product of the signal with a unit phasor for a particular frequency index. To get back, you actually have to look at all the coefficients for every frequency index and multiply them by the phasor sampled at that sample, sum them all up. What's interesting is these two formulas look pretty similar for forward and inverse. So you can use the same algorithm to implement both forward and inverse. But anyway, fine, so that's a DFT. It's been a little longer since we've done convolution, so let me actually derive or just come up with a formula for that real quick. So let's say, suppose we have a signal x and with n samples, and we have an impulse response h of k with k samples. Then we compute the convolution. Well, let me not use k. Let me say maybe h of j, because k is already used for frequency index. Okay, so impulse response hj with j samples. Then we compute the convolution, which is denoted as x asterisk h of n, as follows. So x asterisk h of n is equal to, well, let's think about this. So I have a bunch of lags that add together into a superposition. So let me sum over all the indices in the impulse response. Let's say from j is equal to 0 to big J minus 1. Okay, so the impulse is going to come back with a value of h of j. But actually the whole thing has been lagged. So it's x, but it's been lagged by an amount of j. So this would actually be x of n minus j. So it starts j in, so the nth sample for this particular echo at h of j happens at x of n minus j. Okay, so this is the formula for convolution. All right, so we'll return to that in a second. Let's just do some experiments first. So what I'm going to do is I'm going to take in a signal. I'm going to take in its impulse response. And I'm just going to look at, so I'll compute the convolution. I'm going to plot the Fourier transform of the original signal, discrete Fourier transform amplitudes or magnitudes of the complex numbers. I'm going to plot the Fourier magnitudes of the impulse response. And then I'm going to plot the Fourier magnitudes of the convolution, and we're going to look at the result. So let's load in that robot sound.
I am a robot.
Okay. Let me now set up a comb filter. So let's say I'll make it just a second long. But I'll say, let's see, I'll make my period be 100. So we know that if the sample rate is 44,100, then the frequency would be 441. We know that from our experiments before. So let me just make the first maybe 10, I'll do 10 repetitions of the spike. Okay, so that'll be my impulse response. And so now let me call this, that'll look at Fourier transform of x, Fourier transform of impulse response, and then the Fourier transform of the convolution. And also let me listen to the result just so we remember what that sounds like. Okay, so the results, here it is.
I am a robot.
Okay, so again, I was able to sort of pitch my voice by convolving. By the way, convolve, that's the verb to perform a convolution. Okay, so here's the Fourier transform of the original, Fourier transform magnitudes of the original signal. Now what I've done here is I'm displaying this on a log scale, because remember, we actually perceive loudness on a log scale. It's also going to make a few features stand out. Here's the Fourier transform of the impulse response. So we see something pretty interesting, which we kind of empirically observed before. This thing peaks at 440 or 441 and every multiple of 441. So we get these harmonics. That's why it ends up sounding pitched. Okay. But then, okay, look at the Fourier transform of the convolution. So it looks like the original signal multiplied by the Fourier transform of the impulse response. So see how it peaks? Like it's kind of been shaped by this thing. So it peaks here, and then it peaks here, and then it peaks here, and then it peaks here. So it has all these local peaks that coincide with the peaks of the impulse response. So that's pretty interesting. And just to show you, if I change the impulse response, so let's say that I make it a width of 50, then these are going to spread out a little more.
I am a robot.
And so I see the peaks occur here. Actually, I need to make, in order for this to really stand out, I need to make more of these. Okay, so you see now at 880 and 1760, I get these peaks.
I am a robot.
Okay, but it was a little clearer going back to this one. Okay, and also the other thing you notice, just as a side note, if I include more pulses in the cone, then these things stick out even more.
I am a robot.
So what you're seeing is actually, and what you're hearing is the more pulses I include in my cone. So if I'm including 50 teeth, the more that these frequencies stand out.
I am a robot.
So here it gets a little clearer. Yeah, let's do like 200. Yeah, so now these are really standing out from the other frequencies. You can see them really peaking there.
I am a robot.
And now it's almost like a constant pitch. It really killed kind of almost everything else. But if I go down to just like 5, then these don't really stand out as much.
I am a robot.
And you hear a little more of my original voice. Okay. All right, I just want to do one more example, which is an example of something called a low-pass filter. And so that is, what you can do there is I'll say, okay, H is equal to MP.0's SR. If I make the first so many samples of this, let's say from 0 to 100 to be 1. This is interesting. I'm saying I get a whole bunch of echoes, like really in rapid succession, and then nothing. Starting at the beginning. That's the way to interpret that, thinking about that as an impulse response. But what does it actually do when you listen to it and when you look at the Fourier transform? Well, okay, so here's the Fourier transform. Now, what you kind of notice is, yeah, this is actually going a little further down than I want. Let me say plt.ylim 1e negative 5 1 is good, I think. It's sort of distorting the feature that I want you to see. Let me try this again. Okay, so we got this. Let me go a little higher. Let me go up to, oh yeah, I could go up to 10 squared. Okay. Oops, I need to do that here too. Okay. I'm just trying to get this into a good range where I can show you what's really happening. Okay. Still missing one, hang on. I need to do that here, I need to do that here. Looks like I'm not seeing that. Oh, I just need to go a little more. Let's go up to 1,000. Okay. Almost there. Okay, fine, good enough. So now let me look at this down here. Okay, so what I see is that the frequency starts to decrease as I go, or the amplitude or the magnitude of the frequency starts to decrease of the impulse response as I go up in frequency. And what that does is that in turn turns down. Actually, let me do the following. Let me say H is equal to H over MP.sum H. Okay. Now this is back in the range I'm going to look at. Okay, so what this does is this slowly damps off the higher frequencies. So what does this sound like?
I am a robot.
Can't really hear too much different now. Let me make the first 1,000 samples be like that. So now you see it really falls off.
I am a robot.
So, and actually let me make X a little different. Let me actually make X noise. I'll make X to be 2 seconds of noise. So if I go back and I make this really short, I don't get that damping so much. That's sort of noise over the whole spectrum. But if I make this a little longer, I do more averaging. That's what it ends up being. I can hear that the noise has gone down. It's become a little muffled. If I go even more, I can see that the frequencies are going down even more. So I get even lower in frequency. But anyway, the overall thing we're noticing, which is very interesting, is that the amplitudes of the convolution are the product of the amplitudes in the original signal and the amplitudes of the impulse response. So let's take a breath and absorb all that. And now I'm gonna prove this in the next video.